Hi everyone, welcome to the Probability and Analysis webinar. It's my pleasure to introduce today Varun Jog, who's gonna speak about reverse isoperimetric inequalities. Please, Varun.
Okay, yeah, thank you for the invitation. Happy to give the talk. Yeah, the title of my talk is Reverse Euclidean and Gaussian Isoperimetric Inequalities for Parallel Sets with Applications. To start with, what is an isoperimetric inequality? Turns out that this question has roots in mythical tales. Like there was a queen, Dido of Carthage, who was apparently escaping from Europe somewhere and landed in Africa. After her murderous brother Pygmalion killed her husband or something. So she landed in Africa, and then she was negotiating with the king there, King Hiervas, about buying a piece of land. And I believe he told her that she can get as much land as can be encompassed by one ox hide. And of course, she took the ox hide and cut it into thin strips. And now she was faced with the isoperimetric problem that you want to encompass the largest possible area for a fixed perimeter. So you have the length of the ox hide is fixed. So what is the shape that encompasses the maximum area for a fixed perimeter? And that's the isoperimetric problem in 2 dimensions. So in 2 dimensions, you can also write the problem as an inequality that if L is the perimeter, then L square is greater than 4 pi a. So and equality is achieved by the circle. The first proofs of this inequality appeared in the 19th century. So although this is quite an intuitive result that one would immediately think that the right shape is a circle, the first proofs actually had to wait until the 19th century when Jacob Steiner proved it using symmetrization arguments. There was a small gap in the proofs about some existence of an optimizer, but that was fixed again in the 19th century by Weierstrass. So having proved the result in R2, the natural question is what happens when you go beyond R2 to RD. Things become a little bit tricky in RD because the notion of set surface area is harder to define there. But let's say you define surface area as follows. So this is the definition of what is called the Minkowski surface area. So you take any set A, any say measurable set A, and add a small ball to it. So B here is the Euclidean ball in 2 dimensions, the unit ball. So you take A and you take the Minkowski sum of A with a small ball and see how much the volume increased in the first order of magnitude of delta. So this quantity, intuitively, it makes sense, like this should be the notion of surface area. And if you use this definition of surface area, then you can write the Euclidean isoperimetric inequality. So this says that the surface area of a measurable set to the power d is greater than something. So on the something you have lambda of a, which is the volume, which is just the Lebesgue measure of the set. So lambda, I forgot to mention, is the Lebesgue measure. And you get the same result that you get equality if and only if the set is a ball. And it is non-trivial to prove. So again, just as the 2-dimensional one, one might think that this is a natural result. It's non-trivial to prove it. And one approach uses the famous Brunn-Minkowski inequality, which is shown below. So you basically use this inequality where B is replaced by delta B, where B is the unit ball. Right, so once you have the notion of isoperimetric inequality, you can go beyond the Lebesgue measure and ask, well, do you also have similar inequalities for, let's say, the Gaussian measure? And the Gaussian volume is defined just as the measure of the set under the Gaussian measure. The Gaussian surface area is defined as shown on the slide. It is basically identical to the definition as before, except the Lebesgue measure has been replaced by the Gaussian measure, gamma. So it was shown, and the isoperimetric problem is that, let's say you have a fixed surface area and you want to maximize the Gaussian measure of a set. So around 1975 and 78, Borel and Sudakov and Cyrilson independently showed that half spaces are optimal for the Gaussian measure. So the place of balls is is now taken up by half spaces. And this will also generalize later to different kind of log concave distributions as well. So I'll probably come back to that. Okay, so this talk is not about isoperimetric inequalities. This is about reverse isoperimetric inequalities. So what do I mean by that? So what if you have a fixed volume and you want to maximize the surface area of a set? So this seems like the naive way one would rephrase a reverse isoperimetric question. But you can see that after a bit of reflection that this doesn't always make sense, because you can have really weird shapes that have massive surface areas for no volume, right? So you can have this like coronavirus shaped like object, which can have like a fractal like structure essentially, and it can have a huge surface area for the same volume. And an even simpler example would be something like just a shell. So a shell has zero volume, but it has as big a surface area as you want. So this question doesn't always make sense if you allow all possible sets to be used. So what if it disallows such sets? So we have to now be careful in saying, well, what are such sets and what kinds of sets would you want to look at to prove isoperimetric inequalities, reverse isoperimetric. So I'll give one example. So this is a very well-known inequality, which is the reverse isoperimetric inequality in the Gaussian setting for convex sets. So once you have convex sets, you no longer have such really wiggly boundaries. So that naturally poses some constraints on what kinds of sets you can use. So the result that was showed by Keith Ball in '93 was that you can take any arbitrary convex set in RD, then its Gaussian surface area is upper bounded by 4 times d to the 1/4, where d is the dimension. So of course, this is independent of the bounded. You don't need the set A to be bounded or anything. This is true for all convex sets A. The bound was shown to be essentially tight by an explicit construction. So you can construct convex bodies that have a Gaussian surface area of some constant times d to the 1/4 as well. And these results were generalized to certain kinds of log concave measures by Lifshitz. Now, if you want to get reverse isoperimetric inequalities for the Lebesgue measure in the Euclidean setting, then you can see that maybe just having a set to be convex also doesn't quite. You can have a really flat sort of a set which can have a very large surface area with a very with a tiny volume. So you have to have, so you can impose some kind of a curvature condition. So you disallow wiggliness of the boundary. So there were, so the most natural idea is kind of to restrict the, what is called the average curvature to something less than 1. So in R2, if you have this kind of an average curvature constraint, then Howard and Dryburgh showed that if the area is sufficiently small, then the peanut shape that is shown on the slide is somehow optimal. And in arbitrary dimensions for convex sets, under a certain notion of not the average curvature notion, but a slightly different notion of curvature, this recent result by Chernov, Drak, and Tatarko showed that there is an optimal sausage body. So the sausage body is essentially the Minkowski sum of a Euclidean ball with a line segment. So this body turns out to be optimal in that it will have the maximum surface area for a fixed volume. Right, so it's kind of tricky to prove reverse isoperimetric inequalities because you can't really guess that this is what is going to turn out to be the optimal shape. Unlike regular isoperimetry, where you could say that the spheres or balls are optimal, reverse isoperimetry, there is no obvious contender for optimality, which makes these questions harder to answer. Right, so in this talk, I'm going to look at a different kind of a curvature. It's not exactly a curvature condition, but a different kind of restriction that allows me to kind of not look at all these really sets with wiggly boundaries. And that notion is what's called parallel sets. So a parallel set is essentially just a thickening of a set. You take a set A, and then look at all the points that are at a distance r from the set A. So you start with an A and just sort of thicken it by r. So the notion of the metric here could be any metric, but in this talk I'll only focus on the L2 and the L infinity metric. So I'll denote by A circle plus R as the set A plus, so the parallel set with respect to the Euclidean ball, and A box plus R to be the parallel set with respect to the cube, n-dimensional cube, which is essentially the unit ball in the L infinity norm. Right, so what do these operations do to a set? Well, you can think of it as a different way of smoothing a set. So if your original set A was something like a star with many pointy corners, once you smooth it with a ball, it no longer has that many pointy corners. It sort of smoothens the edges, kind of corners of the set. But it doesn't give you everything. Like you still, the set that you end up with can still be, is going to be non-convex. It can still be non-convex, and its boundary can have many bumps. So it does smooth the boundary, but not in a very natural or easy to describe way. So why am I considering parallel sets in this talk? Well, there are three main motivations. One is that parallel sets are by themselves very crucial or important in convex geometry. They show up in Steiner's formula for the volume of a set plus a ball. They are which is related to intrinsic volumes, and the coefficients of Steiner's formula are related to intrinsic volumes and square mass integrals. So that's one. So these parallel sets are kind of already there and well studied in geometry. The second motivation for me was information theory. So I come from an information theoretic background. And in information theory, there is often this trick that we use of Gaussian smoothing, basically. So if you want to prove some kind of an entropy inequality, you always take the random variable, add a little bit of Gaussian noise to it, so that its density is now suddenly very well behaved. And then you prove whatever inequality you want to prove, and take the limit as the smoothing is going to zero to prove your result. So on the geometry side, it seems like a natural thing to do. So if you're adding a small Gaussian, then on the geometry side, maybe what you should be doing is taking the set and adding a small ball to it, the Minkowski sum with a ball. And the third motivation was some problems in theoretical machine learning. So these were the problems that actually got me thinking about parallel sets. So at the end of the talk, I'll present what were the specific problems that, what are the specific applications of these inequalities in some machine learning problems. Okay, so here's the problem statement, what we want to prove. Just take an R parallel set with a volume at most V. So the set A plus R, A circle plus R has volume V. How big can its surface area be? So clearly the surface area has to depend on both V and R. It will depend on V because the larger the volume, larger the surface area you could have. And it will also depend on R because smaller the R, the fewer restrictions you have on the wiggliness of the boundary. So whatever bound you are going to get is going to be directly proportional to V and inversely proportional to R. In some not exactly linear, but in some way it's going to be directly proportional to V and inversely proportional to R. And then we ask the same question about A box plus R, so parallel set in the L infinity norm. And we also ask the same question now for the Gaussian measure. Is there any way you can upper bound the Gaussian surface area of A box plus R and similarly, A circle plus R and A box plus R. So in the Gaussian case, we don't need to say that the volume is at most V. We just say that here's a set. How big can its Gaussian surface area be? Okay, so I'll just first tell you the results and then go on to some description of the proof. So what happens in the Euclidean setting? So turns out that we can prove the following result. So bullet points 1 and 2 kind of show the main results that if the volume of the parallel set is at most V, then its surface area is at most some constant times V over R. So as I said, it does eventually turn out to be directly proportional to V and inversely proportional to R. But that constant here, at least in the proof that we have, happens to be exponential in the dimension. So e to the theta of the e to the some constant times t. And the same result happens to hold for parallel sets in the L infinity norm as well. Right, and the result that we can prove in the Gaussian setting is kind of is as follows. So in bullet point 1 and 2, that the Gaussian surface area of any set, any R parallel set, is upper bounded by max of some constant and the constant over R. So there is a reason why there is a max term there, because recall that a half plane or a half space has a Gaussian surface area which is actually a constant independent of dimension, and a half surface or sorry, a half space can also be thought of as an infinite parallel set of some other half space. That's why you can't expect your upper bound to go down to 0 as R goes to infinity. So that's why you get this max term between a constant and constant over R. Okay. So here's the outline. I'll give a proof sketch of the Euclidean and Gaussian inequalities. And then as an aside, kind of just show that some of the proof techniques that we use give rise to some reverse Brunn-Minkowski and reverse entropy power inequalities. And at the end, I'll discuss some applications to theoretical machine learning, and then present some open problems. Okay. So I will pause here if you have any questions. I can't actually see the chat window while I'm sharing, so in case there are questions, feel happy to just speak out. Okay, I will move on.
So Varun, I have a question actually. What you're bounding from above is the surface area of the parallel body instead of its volume. Is that correct?
Right. I'm bounding the surface area of the parallel set in terms of the volume of the parallel set.
Okay. So that's a little different from what one might naively think of as the reverse isoperimetric inequality, right? Because bounding from above the surface area of the original set is like bounding from above the volume of the parallel set. I mean, because the surface area is defined as the, if you don't worry about the limit in the definition of the surface area, you're essentially bounding from above the volume of the parallel set, right? So you're doing something slightly different.
Let's see. So, right. So I'm kind of saying that the class of sets I'm allowed to consider are measurable sets that have already been thickened by some fixed R. So, so instead of kind of imposing some kind of a smoothness condition on the boundary, I'm saying, well, I want to get rid of sets with wiggly boundaries. So the class of sets that I'm allowed to look at are sets that have already been thickened by R.
Yeah.
And for those sets, the way you define the surface area is that you then, those sets have already been thickened by R, but then you thicken them a little bit more by delta and then take the limit.
Okay, sounds good. Thanks.
Okay. Good, thank you for the question. So, right, so the main steps in our proof are, we'll first show that, of course, so parallel sets, as I said, are essentially the Minkowski sum of a measurable set with a ball. But you can show that it's enough to consider finite unions of balls. So the original measurable set can just be some kind of a collection of points. And this follows from a very nice paper from 1976 by Laszlo Stasio. You can use some kind of a limiting argument. Once you have shown it for finite unions of balls, you can use a limit argument to show that it will hold for all bounded sets. And then the second step is kind of our key lemma. So this is going to be some result concerning certain, for lack of a better description, I've just written some geometric substructures. But this is kind of lies at the heart of the argument. So once you have this key lemma, then the third step is a packing argument. So you say that, well, if you give me any parallel set A sub R, it can only have so many geometric substructures, and then you kind of conclude the Euclidean inequality. And to go from, once you prove the Euclidean, there's a very nice trick again in Ball's 93 paper, where he proved the reverse Gaussian inequality for convex sets. So you can use this nice trick to go from the Euclidean setting to the Gaussian setting. So you can get a bound in the Gaussian setting. Okay. Right. So here's.
Can I ask a question?
Sure. Yeah.
The first step, that it's enough to consider finite unions of balls. Mm-hmm. Is it the one that gives you the big constant in front, or that comes from somewhere else?
I think that is coming from the packing argument in the third step. So at some point I have to use a packing argument, and the bound that I use for packing is some volume divided by volume of a ball, and I'm getting this exponential constant there.
Okay, thank you.
Yeah, thank you. Right. So here's this substructure that I'm going to discuss. So I'll call it the puzzle B, and then I'll also present a puzzle C. So B is for ball and C is for cube. So what is puzzle B? So let's say you start with a circle. So in this, let's say in 2 dimensions. So you start with a circle, the blue circle in the slide, whose center is x0. Now, you take a bunch of points, x1, x2, dot, 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 xn, however many points you want, and put those points inside the original blue circle, and then put a unit circle again. So the original circle is also a unit circle. So you put unit circles centered at x1, x2, and dot, 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 xn, and take the union of all the circles that are there in the picture. So, so what you get at the end is this red region, which has this bumpy boundary. And the puzzle is, can you show that the perimeter of this red region is upper bounded by 4 pi? So 4 pi also happens to be the perimeter of the circle with the radius 2, which is the dotted circle. So we essentially want to show the perimeter of the red bumpy region is at most the perimeter of the dotted circle that I've drawn. So this kind of I thought this was an interesting kind of puzzle to look at. So this red region that you get is not immediately like a very nice figure, and it has a lot of bumps, so you can't immediately say something about what its perimeter is going to be. So this was one problem that I was looking at. And I'll also state what is the puzzle C. The puzzle C is the same puzzle, but now you replace unit balls by unit cubes. So not unit cubes, these are cubes with unit radius in the L infinity distance, which means they have side 2. And you do the same procedure. You start with one cube or a square centered at x0. You take a bunch of points inside the original unit square and put squares on top of that. And again, look at this, the union of all the things that you see, which is now this set with vertical and horizontal boundaries. And our goal is to show that its surface area is upper bounded by, its perimeter is upper bounded by 16, which happens to be the perimeter of the square of the L infinity ball of radius 2, which is the perimeter of side square. Okay, so these are the two puzzles that I want to look at, and somehow these hold the key to the whole problem. Okay, so any questions about the setting of the puzzle?
There's no requirement here that the shaded region is connected, right?
Yeah, there's no requirement here.
What's the size of the original square?
I'm looking at sort of unit balls in the L2 and L infinity. So here the original square is, the side is 2. So the corners are 1, 1 and minus 1, minus 1 kind of, if x0 is 0, 0. Okay, All right, so I'll first give the solution to the first puzzle, the puzzle with the balls. So the one observation is that the set that you get, you can show that this is a star-shaped region. So what does star-shaped mean? It just means that any ray that you draw from x0 will intersect the boundary of the set in exactly one point. Right, so once you know that it's star-shaped, then what you do is you break up the boundary into chunks. Right, so I have broken down the boundary into these kind of chunks from contributions from various circles, and then I use the inscribed angle theorem. So let's say I'm looking at the lowermost chunk in the figure. Then the angle subtended to its center is theta, and angle subtended to the original x0 is phi. So it's really easy to show that phi is actually greater than theta by 2. So if x0 happened to lie on the boundary somewhere, boundary of this circle, then you would have got an equality. But since x0 is inside, you get an inequality. And the original perimeter is just the sum of all these thetas. So how much does each chunk on the boundary subtend towards the center of its ball? So the perimeter is the sum of thetas, and that is upper bounded by twice the sum of the phis. But the sum of the phis, which are all the angles subtended to x0, is going to turn out to be 2 pi because our set is star-shaped. And that gives you the result. So this inequality, you can actually check that equality is achieved by, in many situations. You just need to make sure that all the points that you take are on the boundary of the original blue circle. And you, in most situations, as long as they're not all bunched together on one side, you end up getting equality. The solution to the puzzle C is actually easier, so I won't go into details, but you can essentially show that the set that you get is going to have only vertical and horizontal boundaries. And every vertical line intersects the boundary in either 0 points or 2 points. So it is kind of convex. It's not really convex, but if you look at axis aligned lines like vertical and horizontal lines, then you know that they will intersect in at most 2 points, as long as that line is between the dotted square that I showed. And this observation kind of immediately gives you that if you project this object onto the x-axis, you will count each chunk sort of at most twice. So the sum of all the horizontal segments is at most 8, and sum of all the vertical segments is at most 8, and then you end up getting the boundary. So it's not as involved and kind of follows in a straightforward manner. So this proves this solves the puzzles in 2 dimensions. What we want is some generalization of these puzzles to d dimensions, right? So I say that going from R2 to RD for this cube problem is very easy. You just do the same argument, except instead of just horizontal and vertical lines, you now have d dimensions. Like you need to consider lines parallel to each of the axes one at a time, and do a similar argument. Okay, so what upper bound do you get? You get an upper bound, which is the surface area of the dotted cube, which is as shown on the slide. Now puzzle B, the ball puzzle in RD, is kind of interesting because we use the inscribed angle theorem in R2. So the natural question is, well, is there an inscribed angle theorem in RD which we can just apply? And I didn't know the answer, which was, I mean, it seemed like something that I would have learned in school, but I never learned this. But this is because there is no inscribed angle theorem in RD. But you can get an inequality in the right direction. So here's my attempt at explaining in a picture what exactly happens. So let's say you have a small, let's say this is a circle with center x1.
It's
and
15:30.
And you have a small section of the boundary, which is and now you're looking at that small section of the boundary from the point of view of x0. So if you're looking from x0, there are 2 things that happen. One is that small region of the boundary is at a different distance away from you. And also you're no longer looking at it sort of perpendicularly. So what you see is a projection of that the original shape. And both of these affect the solid angle. So it turns out if you were to calculate the solid angle, it depends on some angle theta. So depending on where this point x0 is located, you get a different solid angle which is subtended to the boundary. But what you can show is that the solid angle subtended towards x0 is the solid angle at x1 divided by this quantity 2 to the d minus 1 cos to the d minus 2 theta. And it just so happens that in dimension 2, the d minus 2 goes away and you get exact equality, like independence of the theta. But in higher dimensions, that theta does play a role. But of course, cos theta is at most 1. So you still can get an inequality, which is that the solid angle at x0 is larger than the solid angle at x1 over 2 to the d minus 1. And this inequality goes in exactly the correct direction that we want it to go. And you end up getting a bound, which is the surface area of the sphere with twice the radius. So that's the quantity that I've written here. So capital omega d is the surface area of a unit ball, and it is 2r to the d minus 1 times capital omega d. So this kind of translates both the puzzles from R2 to RD. So all right, so what do we do with these puzzles? So this is where this packing argument shows up. So let's say you have, I apologize for the picture, but this is the best way I could try and explain it. So let's say the original set A sub R, this is the finite union of these balls of radius R. So what we do is we try to express the original set A as some kind of a union of these substructures that I've been talking about. So what you do is you start out with some ball, let's say the blue ball, and you look at all the points who happen to lie inside the blue ball, and you take the circles that were centered at those points and make that the blue substructure, and sort of keep it aside. Now you look outside and see, well, are any other points remaining? Well, it turns out the pink point was not included inside the solid blue ball. So you take the pink point, and then you draw this pink ball and look at all the points that are now sitting inside the pink ball, but not that have not already been accounted for by the blue ball, and you get 2 more circles that join the pink substructure. And you look again, well, are there any other points remaining? Turns out, well, there is a red point remaining. You take the red ball, look at all the points who happen to lie inside this red ball, and look at the balls centered at those, and that gives you the red substructure. And what we notice is that the original boundary of this set, which is something really complicated, so that boundary is a subset of the blue boundary and the pink boundary and the red boundary, which means the original surface area or perimeter is upper bounded by the sum of the perimeters of each of these substructures. And the puzzle that we solved kind of bounds the surface area of these kinds of objects. So if we can just upper bound how many such substructures are there in the original set, then we can just multiply our bound to the number of substructures and get a desired upper bound on the surface area of the original set. So that leads to the question, how many substructures are there in the parallel set? So I didn't really use any super complicated tools here. I just said, well, the volume of the set is V, and this packing argument ensures that the blue ball and the blue point, the pink point, and the red point, they are all at least a distance r/2 from each other, because if not, they would be inside each other. So that gives us that, well, the total number of such points has to be volume of the set divided by ball of radius r/2. So that kind of gives me the bound. So at the end, as I said, the surface area of each substructure is at most this quantity. The number of substructures you can pack is at most this quantity. So the surface area that you can get of the original set A plus original parallel set is just a product of these two quantities, which happens to be this exponential constant times V over R. Right, and so that completes the Gaussian trick. Sorry, that completes the proof in the Euclidean setting. In the Gaussian setting, this is where we use Ball's trick. So it uses this identity that e to the magnitude of x squared by 2 is the following integral. And this integral allows you to think of the Gaussian surface area as some kind of a weighted Euclidean surface area. So let's say you have this set A and you want to calculate its Gaussian surface area. The way you can calculate it is you take a ball of radius tau, look at how much of the region of A happens to lie inside the ball of radius tau, take the surface area of the blue, so basically the blue regions or blue perimeter that I see, and weigh that quantity by tau times e to the minus tau square by 2 and integrate the whole thing. So as your radius tau increases, you encompass more and more of the surface area of the object A, but you weigh it less and less, and eventually when you integrate the whole thing out, you get the Gaussian surface area. And now, since we already have a result for the Euclidean surface area of parallel sets, to go from Euclidean bound to the Gaussian bound, we essentially just take the bound on the Euclidean surface area, plug it in here and integrate. And I'll skip the details, but the integral just happens to be this maximum of some exponential constant and some exponential, and the same constant divided by r. Okay, so I'll maybe pause here for a few seconds if there are any questions. Okay, right, so then I'll move on to these two asides about the reverse Brunn-Minkowski. So again, I'll take it with, I'm kind of hesitant to call it a reverse Brunn-Minkowski inequality because it's more of a property of the parallel sets and less of some deep property about Minkowski addition. It's more of a consequence of the regularity conditions that are imposed because of the considering parallel sets. So this is the regular Brunn-Minkowski inequality, and proving a reverse inequality is problematic because of examples like these, when you can take two volume zero sets and add them and suddenly you get a set with a volume. But if you allow, if you're only using parallel sets, K sub r and L sub r, so here I don't really care what those, it can either be the L2 or L infinity. If you use K sub r and L sub r, then you can use some of the techniques that we had used about the packing arguments and get an upper bound that the volume of K sub r plus L sub r is upper bounded by the product of the volumes, which seems weird in terms of the dimensionality, but then you divide it by another volume term. So it's a volume times volume over volume of something else. Right, and so that gives you a bound. This got me interested in whether something similar holds in the information theory world, that if you were to take random variables and add Gaussian noise to it, then can you prove some similar inequality? So the analog of the Brunn-Minkowski inequality is the entropy power inequality, which gives you a lower bound on entropy of x plus y when x and y are independent random variables. You cannot reverse it in general because of similar issues that happen in the Brunn-Minkowski inequality. But if you ensure that your random variables are Gaussian smooth, so smoothed by small Gaussian with, let's say, variance r, then what you can show is that the entropy of xr plus yr can be upper bounded by h of xr plus h of yr plus some constant that depends on the smoothing. So if your r is very small, then the constant is huge, which makes sense because you're not smoothing that much. Yeah, so this inequality is kind of tight. Like if at all it is loose, it's loose in by a constant. But this is something that we were able to prove. And all right, so I have about 10 minutes left. So I'll go to these applications to machine learning. So this was kind of what got me interested in this problem in the beginning. So the first application is what is in this kind of learning sets. So the problem setting is that let's say you have some set which is subset of RD, and you want to figure out what the shape of this set is. But the kinds of questions that you can ask are just, you can sample a random point according to the standard Gaussian measure, and you can ask the question, does this point belong to the set or not? And you can ask many questions, and for some of these points you'll get an answer yes, for some of these you'll get an answer no. But looking at the answers, you want to then say that, well, I think the shape is approximately this. So approximately means that the difference of the set that you estimate to the actual set in the Gaussian measure is as small as you want, like smaller than epsilon. So you want to, of course, find the minimum number of questions you need to ask to learn that set. Now you need to define this problem well. You have to figure out what is the class of sets that you're allowed to have. Because if you allow all possible measurable sets, then you will never be able to find it, no matter how many questions you ask. But if you restrict the class of sets to some reasonable family, let's say convex sets, or I don't know, half planes, then you can solve these questions and get a bound on how many questions you need to ask. Right, so the complexity measure is what is the measure by which you are restricting the class of sets that you're considering. So in this, in a 2008 paper by Adam Clavens and collaborators, they showed that the Gaussian surface area can be thought of as a good complexity measure. So if you have sets that have a small Gaussian surface area, then that means they are not very wiggly, which means you should be able to learn them. And in fact, they showed that if you can bound the Gaussian surface area of sets, then that leads to a bound on the computational complexity. So that gives us a bound on how many samples n one would need. And since our results kind of gave us a bound on the Gaussian surface areas of our parallel sets, you directly get learning bounds, computational complexity bounds for learning these kind of sets. The second application to machine learning is motivated by adversarial machine learning. So this might be an example that you have seen several times. But so what happens in adversarial machine learning is you train, you have a huge data set and you train a neural network to kind of classify everything correctly. But then you give it an image of a pig that is currently being correctly classified as a pig. And then you add a little bit of noise. So this noise has been added carefully. It's not random noise. And then you get an output image, which to a human being looks exactly the same as the input image. But your deep learning classifier is going to now classify it as an airliner, which leads to the joke that machine learning can make pigs fly. So these kinds of examples are they're all over the place. Like it's not, you don't have to search hard to find such examples where adding a small amount of noise gives you a completely wrong answer. And of course, the questions that people are currently thinking about is, well, why do these errors occur and how to avoid these? So with a student last year, I was thinking about these problems more from a hypothesis testing framework. That, well, let's say you have only two categories, like class 0 and class 1, and you're just testing, you're giving an answer whether the sample that you've seen lies in class 1 or class 0. So what we want to output is some set A, which where if the sample that you observe happens to lie in A, then we are going to declare class 1. Otherwise, we'll declare class 0. This is the really classical hypothesis testing setting. And in this setting, you know that risk is given by half of, let's say the probability distributions are P0 and P1, and each class is equally likely. Then this is what the risk is given by for a particular set A. Now, what happens in the adversarial setting is you get a risk, you kind of, if the point that you get happens to lie on the boundary somewhere, then an adversary comes and pushes it across the boundary. So you also make errors in a boundary region around the set A that you declare as the correct region. So the risk or the probability of error turns out to be related to these thickened sets. So your original set is A, and A sup epsilon in the setting is the parallel set, essentially. And A complement sup epsilon is the parallel set of A complement. So this was very interesting because these parallel sets are showing up naturally in this adversarial setting. Right, so what we, with a student, what we were looking at is, well, can we study this adversarial problem kind of like a hypothesis testing problem and characterize what the optimal adversarial risk is going to be. And so we know in the hypothesis testing framework, the optimal risk is base risk, and base risk is half of 1 minus total variation. In this particular setting, you get half of 1 minus not total variation, but some other quantity that is very much like total variation, but it's not a metric. So it turns out to be a version of an optimal transport cost between the two distributions, where the cost is basically indicator that the distance is greater than 2r. So if you are moving by more than 2r, then you incur a cost of 1. If you're moving by less than 2r, you incur a cost of 0. Among all such transport plans, take the best transport plan, and that happens to give you the adversarial risk. So this kind of was known by last year. And what I was thinking about was, well, if you want to actually apply this result and look at real world data sets and say, what is the fundamental bound on adversarial risk? What is this quantity d sub r on the real distributions? So we never really know what the true underlying distributions are. All we see in a data set are samples. So what we see are the empirical distributions. So you might ask, is the estimate of this optimal cost that I get from the empirical distributions close to the estimate, close to the true optimal cost between mu and nu? And how many samples do you need to get, let's say, epsilon to maybe get very close to the true quantity? And are there any rates that we can come up with? And I won't go into the details, but if your data distributions mu and nu are assumed to be Gaussian smooth, then the Gaussian reverse isoperimetric inequality ends up giving you such bounds. Like how many points do you need to estimate d sub r, because estimating d sub r allows you to estimate kind of the information theoretic limit of what's the best you can do in the adversarial setting. Right, so I'll end with a few open problems. So the first is in both the results for the Gaussian inequality and the Euclidean inequality, this constant that shows up there is exponential in the dimension. And if one is really optimistic, one could say, well, is the constant actually independent of the dimension? Because that's what happens when you're looking at half spaces. I doubt that it is dimension independent. But if it is dimension dependent, what is the correct dependence? Of course, to show it is dimension dependent, one would have to come up with an example where it is where you can show that, let's say, the Gaussian surface area is increasing with the dimension, and what is the correct kind of dependence on the dimension. So I don't quite know the answers to either of these questions. The second is, so the results that I showed were for Euclidean balls and cubes, and it used the geometric properties of balls and cubes quite heavily, like things like inscribed angle theorems, or the fact that balls or cubes only have vertical, horizontal, or axis-aligned line of regions on their boundary. But is it possible that these are just examples of more general results that hold for all symmetric convex sets? So you start with an arbitrary measurable set, you smooth it by some nice symmetric convex set, and then these kinds of results have to hold for parallel sets of that form as well. And the third question is there any way to approach these results from the analysis side? Like, I just feel it's kind of odd to have a result where you're using things like inscribed angle theorem. There must be a way to prove these results starting from some more abstract notions of some functional inequality which implies these. that might be something worth looking at. Here's the reference, and it's available on arXiv. Thank you.
Thank you very much indeed, Varun, for the great talk. And how about some questions?
So I have a question about the Gaussian setting.
Mm-hmm.
So with the usual Gaussian isoperimetric inequality, you can turn it from an infinitesimal inequality to a non-infinitesimal one by integrating out in R.
Mm-hmm.
I mean, sorry, not in R, because R is something else for you, but you know what I mean, right?
Yeah.
Now, with the rate 1 over R that you have in your Gaussian version, I think you can't really do that for a very long distance, right?
Yep. Yeah.
Right.
Yeah.
But
so I think the way I proved it was proving it for some delta greater than, like proving the result for A sub delta minus A and taking delta to 0. But yeah, for large delta, the bound will become useless.
okay.
So my question is the following. So it reminds me that you have a function, say positive function, on the plane or in RD with compact support, and then you convolve it with some convolution type Bell function, and then you have two things. You have like integral of the original function and the integral of the gradient of the second function.
Mm-hmm.
And you sort of want to, maybe not gradient, maybe something like gradient. And then you want to make the estimate of the second thing by the first thing.
Right.
So this is sort of functional inequality we're trying to talk here.
Mm-hmm. Right. Yeah, so actually the previous question on Joe Neiman, he had looked into, I think, some kind of a smoothing the boundary of a set by really convolving with a Gaussian and then setting some kind of a threshold. So that's also something that I haven't really, I don't quite know how to do. But essentially, like, instead of looking at Minkowski sum with a wall, you look at convolve it with a Gaussian and set some random threshold, and then say that the perimeter of that set is actually small, something. But yeah, I see that the one way to think about a functional version of the inequality is to think of it in terms of function, convolve it, and then talk about its integral of its gradient and upper bounded by the integral of the function. Yeah.
Any other questions? Okay, in this case, we thank Varun once again. Thank you all for tuning in, and see you hopefully next week.